Hello everyone, here we'll be discussing limits and continuity, and of course this is in 3 dimensions. And let's first define limit. So our definition says the following. It's quite a lot to take in, so just kind of bear with me. And first we want to let our function f of xy be a function of 2 variables, of course, such that its domain D contains points that can be as close to the point a comma b that we want. So arbitrarily close just means as close as you need to be. So very, very close, basically. Then the limit as the point xy approaches the point AB of f of x comma y is equal to L if for every number epsilon bigger than 0, there exists a number delta bigger than 0, such that this following statement holds. So this basically is our definition in a nutshell. Everything else is kind of just the setup to that. And this says that if, of course, our point is in the domain D, and this is true, 0 is less than the square root of x minus a quantity squared plus y minus b quantity squared is less than delta, then the absolute value of x comma y minus L is less than epsilon. Now it's a lot to take in, I know, but really what this says, notice, this really is just the distance between, so let me write distance between what? This is just the distance between the points x comma y and a comma b. So we're saying that if these two are not very far apart, then these two must not be very far apart, because the absolute value between the absolute value of the difference between two numbers is just the distance between them. So this is actually the distance between f of x comma y and L. So what this basically says, again, is that if 2 points, x comma y and a comma b, are pretty close, then that means that f of x comma y and L must be close as well. So essentially, as x comma y approaches a comma b, then f of x comma y will approach L. So that's basically what we're kind of saying. And it's kind of hard to visualize this, but just kind of imagine, let's kind of view what happens in 2 dimensions. In 2 dimensions, we're approaching a point A on the x-axis. So you pick a value of x that's close to 8, and then on the function itself, the value, no matter what side you come from, should approach to this point L. So as x values on the curve approach A, so as x values approach A, then the point on the curve will actually approach the y value L. Okay, now it's kind of crooked here, sorry about that. Now, at the same time that in 3 dimensions, what this really says is that x is approaching A, but here, instead we have x, y approaching AB. So we kind of have, on the xy plane, we have this point AB that we want to approach. Here's the y-axis, here's the x-axis, and then up here, of course, we have the z-axis like we're used to now. We'll have some function that has a graph that's a surface. So just imagine that the surface of this graph is somewhere above this point, let's say. Imagine something like this, let's say. I think that's an okay visualization. Then as points x comma y get closer and closer to a comma b on the xy plane, then points on the curve f of x comma y will actually get closer and closer to some z value L. So that's all the statement is really trying to say. And I know it's really precise. In fact, this is known as the precise definition of limit. We actually need it a little bit. Now, I won't really be discussing it too much, but we will actually see an example that involves it. And at the same time, this comes about, this statement below comes about, and it says the following. It says, if we get different things that we approach from different paths, then the limit does not exist. So let me just kind of read precisely. So if f of x comma y approaches L1 as xy approaches AB along path C1, but it approaches L2 as xy approaches AB along path C2, which is a different curve, where L1 and L2, well, L1 is not equal to L2, so they approach different limits, then we say the limit does not exist. Now, if you think of when a limit doesn't exist in a normal kind of f of one variable, so f of x scenario, that's when you consider left and right limits, which makes sense, because notice, if you approach A on the x-axis, you can approach it from the left side of A or from the right side of A. But if you're approaching this point A comma B on the xy plane, you can actually approach it different ways. You can approach it along this curve, along some line, let's say. So for that reason, we actually have multiple different paths we can take when approaching A comma B. And as it turns out, some will give you different numbers than others, possibly. And if that's the case, then we say the limit doesn't exist. So we want it to be the case that the limit is the same no matter which path we take. Just like here, when we want to take the limit as f of x approaches some number L, as x goes to A, we want it to approach L no matter if we go from the left or from the right towards A. So with that being said, finally let's take a look at an example where we'll hopefully see all of this come together. Okay, so for these two examples, they kind of say the same thing, but just a little differently. Here we're asked to show that it does not exist, and here we're asked if it exists or not. So they're kind of different questions, but let's see if we can answer them maybe a similar way. Here we're given that this doesn't exist. So how can we show that? Well, remember that our explanation of when a limit does not exist is that we approach a different limit from different paths. So the path I want to take, and just remember, that of course we're in 3 dimensions, and the paths we're taking are on the xy plane. So really we want to take a look at the xy plane, what path we can approach the 0, 0 from. So either, I think the more obvious ways are you can approach it along the x-axis or along the y-axis. So let's see what that shows us. So let's say we want to approach along the y-axis. Remember the y-axis has equation x equals 0. So if we're approaching along x equals 0 curve, then we just automatically set x equal to 0. And with that being said, our limit now becomes the following. If x is equal to 0, we just get negative y squared over y squared. And this is just going to be the point 0 comma y now, approaching 0, 0. That makes sense? And notice this is just negative 1. This actually cancels out and just becomes negative 1. So here we get negative 1. I probably shouldn't box it, but that's the answer we get. So let me actually circle it. So that's our result along this path. Now if we approach this point 0, 0 from the x-axis, not the y-axis, so let's see if there's a difference. So along the x-axis, maybe you can kind of see that already you'll indeed see a difference. Now of course, similar to how y-axis has equation x equals 0, x-axis has equation y equals 0. And when y is equal to 0 now, this limit becomes a limit as x comma 0 approaches the point 0 comma 0. And moreover, if you let y equal 0 in our equation here, let me use brackets to separate this from the limit, we end up getting the y's are now 0, so we get x squared over x squared, which just collapses to 1. And clearly these are not the same. Since we do not have equality here, this implies that it indeed does not exist, and we have definitely shown that. So it has been shown that you get different results along different paths, so the limit doesn't exist. So hopefully we can show that here, so we can say it does not exist, because I haven't really shown you how to find out if a limit does exist. In fact, all we've really kind of seen was that crazy long definition, and more on that later, but for right now, let's take a look at this. This is going to be a little weird, but let's just kind of imagine, and let me draw the xy plane somewhere over here. So it's the xy plane like we're used to. And we're approaching the point 0 comma 0. And notice we approach from the x-axis or the y-axis in any direction. So we're along that path, those paths. And in fact, in general, you can actually approach this point along any line. Just recall that any line has equation y equals mx plus b. Or in this case, mx, because it's passing through the origin. So it's y-intercept value is 0, so it's just y equals mx in that case. But there's a little bit of an issue, and the only real issue here, as far as lines go, is that the only line that does not have this equation is the y-axis itself. The y-axis has equation x equals 0. But you can see when x is equal to 0, you get y squared over y to the 4th, which cancels to, when x is equal to 0, you just get 0 over y to the 4th. So that's 0 actually. Okay, so we're getting 0 that way. But now what about if we approach by any on any line y equals mx? So let's see, along any line, non-vertical line y equals mx, what do we get? Well, we get the following. our limit now will be going from x comma mx to 0, 0. Y is replaced with mx. So on the top, y squared is m squared x squared times x. So it's going to be m squared x to the third actually. If you square mx, you get m squared x squared, but then times that x gives you x cubed on top. And notice on the bottom, this is going to be m to the fourth times x to the fourth plus x squared. So it looks a little funny, but let's see if we can write it out. Okay, it looks a little weird, but now what's happening is x is approaching 0. I guess something we can do here is we can cancel out a few things, like if you want to factor out x squared from the bottom. We're still in the limit though, so let me just write limit here. And if we pull out x squared from the bottom, we have 1 plus m to the fourth x squared in the denominator. In the numerator we have m squared x cubed. After canceling this x, what do we have left over? We still have an x on top. So actually, as x goes to 0, so remember, really here, this is x going to 0. That's kind of what this turns into. Because if you think of it as x goes to 0 and mx goes to 0, we're really just saying x goes to 0. In fact, if you take a look at mx going to 0 divided by m, x is really going to 0. And you notice since we have an x on top, as x goes to 0, the numerator approaches 0, the denominator is going to approach 1. So this whole thing will actually approach 0 over 1, which is still 0. And I say still because when we were approaching from the y-axis, which is x equals 0, we get the limit of 0 as well. So along any line, even for vertical lines, as it turns out, or the vertical line being the y-axis, x equals 0, we end up getting this limit. Okay, so now what? Well, now we want to see if we can approach from some other curve. Now, what curve and how do we know which curve? This is the tricky part. We don't know. But what I kind of have an idea of is that notice here, we could only pull out x squared because the powers weren't matching. So how can I make the powers match somehow? Well, if you take a look at y to the fourth, that's larger. And in fact, if x was equal to y squared, then x squared would be y to the fourth as well, and they would actually combine into one single y to the fourth. Then we can get cancellation, and then maybe we can get something going from that. So let's go actually along the curve x equals y squared. And yeah, I think this should give us some, this is a sideways parabola on the xy plane, but I think this will give us some actual progression. Let's see. So notice in this case, if x is equal to y squared, then we get y squared comma y approaching the point 0 comma 0 of, now what happens here? Well, in the numerator now, x is y squared, so we get y squared times y squared, which is y to the fourth. And on the bottom, what do we get? Well, again, if x is equal to y squared, we get y squared squared, which is y to the fourth, plus y to the fourth is 2y to the fourth, and look at that. These cancel out, so we just get 1 over 2. And that is a different limit. It's not equal to 0. So since these two actually are not the same, this implies that the limit actually does not exist. And this, I don't know about you, but for me it doesn't make me feel too happy. Because how does this tell us if a limit exists or not? It almost seems like you're going to be trying different ideas and nothing will work until you come up with something clever, and maybe you won't be able to ever tell if a limit actually does exist. So for that reason, we're going to take a look at an example right now where we'll actually see how we can show that a limit exists and what it is. Alright, so as previously mentioned, this is going to be quite challenging. We want to show that this exists and we want to see what it is. So find the limit if it exists. Now to show the limit doesn't exist involved selecting a path, but that would give us an idea. So just selecting an arbitrary path, if it was the correct path or not, if the limit did exist, then it would be equal to that value. It's almost like if the limit does exist, it doesn't matter which path you take, provided you know it exists, which sounds kind of weird. So let's just go along any line. So let's go along the line y is equal to mx. And what we'll notice is that this function, let me kind of bracket this off a bit, if y is equal to mx, the numerator becomes 3x squared times mx, which is 3mx cubed, Denominator will become, let's see, we have mx quantity squared is m squared x squared. If we pull the x squared out, we get x squared times the quantity 1 plus m squared. And notice there's cancellation here of the x's. Like that. And notice as x goes to 0, because we want x and y to each go to 0, because this is really just 3 times mx all over 1 plus m squared, this will actually approach 0 as x goes to 0. Because of course as x goes to 0, mx will go to 0, meaning y will go to 0. So this gives us an idea that maybe our limit is 0 if it exists. In fact, it has to be 0 if it exists, because no matter what path you go along, if the limit exists, you should get the same limit. Okay, so this gave us a really good idea as far as what the limit is. But now, how do we show that it exists? We'll use the definition of limit. Now, if you don't remember, this is what we want to show. We want to show that if the if the distance between these two is less than delta, so we have some distance which is positive, and remember that if this point 0, 0 is our AB, then the distance between these points is x minus 0 squared, which is just x squared, plus y minus 0 squared, which is just y squared. We want that to be less than some number called delta. Okay, then this would imply what? Well, then this would imply that the absolute value between our function, 3x squared y over x squared plus y squared, minus the limit, which is 0, so we don't really need anything, we want this to be less than epsilon. Where epsilon, by the way, is any arbitrary real number. So in fact, this is really for all epsilon. So I know it sounds kind of funny, but basically epsilon represents a really, really, really small number, any number you want, and it could be arbitrarily as small as you want it to be. So 0.0001, for instance, something like that. And delta, as it turns out, will actually be dependent. I didn't mention this earlier, but it ends up being a consequence. The delta depends on epsilon. And it's going to be very kind of difficult in general to show that this kind of relationship holds. And in fact, really what we want is we want to kind of start with this guy here. And since this will depend on delta, I think really what we should be looking for is some connection between these two, this absolute value and this radical. If we can show that this is less than this, then we can show that this is less than delta, or some, delta, or some form of delta. And then we can let delta be some form of epsilon, and then we'll actually be able to maneuver things in a way where we end up getting this result, assuming this is true. So let's work with this absolute value part first. And this actually we can work with quite a bit. So notice if we take the absolute value of the numerator divided by absolute value of the denominator, we'll notice after thinking for a little bit is that the absolute value of 3 is just 3. Absolute value of x squared is just x squared, because x squared is always positive no matter if x is negative or positive. Y may not be though. Y can possibly be negative, so we need absolute value there. Here, very similarly, if x squared and y squared are both positive because they're squares, adding two positive numbers is still positive, so we still get x squared plus y squared now outside of absolute values. Now, what's pretty apparent right away is that we have this absolute value of y, and that's a little finicky. But we have this x squared and x squared plus y squared. And this, I think, kind of tells me something. So if you kind of focus on that x squared and x squared plus y squared, what you'll start to realize is that since x squared is positive, it must be less than itself plus some other positive number, let's say y squared. So since this relationship is clearly true because y squared is positive always, then if you divide both sides by this denominator, or by this number to make it in the denominator on the other side, you end up getting the x squared over the quantity x squared plus y squared is less than 1. How does this help? Well, that means here in this expression, we can actually replace this fraction part, x squared over x squared plus y squared, by 1. So really this is less than 3 times the absolute value of y. And now what? Oh, now we're actually, I think, set. because notice the absolute value of y is actually the same as the square root of y squared. That certainly is true because no matter if y is negative or positive, squaring it gives you a positive number, and square rooting it gives you actually the absolute value of whatever value you started with. So for instance, if y was negative 5, squaring negative 5 gives you 25, the square root of 25 is back to 5, which is the absolute value of negative 5, as it turns out. And very similarly to how x squared is less than x squared plus y squared is also less than x squared plus y squared. And look at that. We are assuming that this is going to be less than delta. So, well, we're assuming this is going to be less than delta. So in fact, this whole thing is going to be less than 3 times delta, because this is part of our assumption in this statement here. So I know it sounds really weird, but we basically what we want to do is we want this guy to be our epsilon. So that's what this implies. If this is our epsilon, then we're set. So now what I'm going to do is I'm going to erase this part, and we're going to let delta equal epsilon over 3. So if delta is equal to epsilon over 3, so for any epsilon value you pick, I'll just let delta be that number divided by 3, then the following holds. Then it must be true that the absolute value of this, which is 3x squared y over x squared plus y squared, must be, well, from all of this work above, it must be less than 3 times delta. So I can rewrite this if you like, but it's not really going to make a difference. So we can take everything outside the absolute value except for the y. And since x squared over x squared plus y squared is less than 1, this is less than this. And since this is actually less than 3 times this, and since we're assuming that the square root of x squared plus y squared is less than delta, then this is less than delta. In fact, this whole thing is less than 3 delta. But since we're letting delta be equal to epsilon over 3, what do you notice? The 3's cancel and we just get that it must be less than epsilon. So I know it sounds pretty weird, but we have shown that this is actually the case no matter which path we go on. So this actually shows that this limit exists and is equal to this. So in fact, the limit is 0 no matter what path we choose. So yeah, in general, it's going to be pretty difficult to show that a limit is equal to a value, unless, of course, we know that that the limit exists. Because if the limit exists, it doesn't matter which path you take, in which case you can always choose the path y equals mx. It's a pretty safe bet. So with that being said, we'll move on to the next idea, which is continuity finally. Okay, so here we'll start to see, again, the definition of continuity for a function over 2 variables, and it'll actually shed some more light on what we saw for limits. So let's go right to it. So a function of 2 variables f of x comma y is continuous at the point a comma b if the following is true. So the limit as xy goes to ab of f of x comma y is just f of a comma b. And this is very often known as the direct substitution property, which is DSP for short. So if DSP holds, then that means that the function is actually continuous at that point a comma b. And then from here we say that function f is continuous on a certain interval, or not interval, but in this case on a certain set d, if f is continuous for every point in that set d. D normally for domain, but it could be something outside of the domain. But normally every function is continuous on its own domain, which is kind of what this leads up to a little bit. And the first 2 things we see are the following. Any polynomial is continuous on all of R2, and any rational function is continuous on its domain. And that'll actually be a very common theme, I think, later on. Now, we'll actually see examples here, these 2 examples, what polynomials and rational functions are, just to remind us. But a polynomial function essentially is any string of addition or subtraction of constant multiples of positive powers of x and y. That was a mouthful, but something that looks more along the lines of this. And similarly, a rational function is a polynomial divided by a polynomial. So it's just a fraction of polynomials, or a quotient of polynomials, if you like. Now, since a polynomial is continuous for every value in R2, then that means we can plug in, well, that basically means that every limit exists. So you can just use direct substitution. So in this case, let's do that and see what happens. So if we plug in 1 and 2 in for x and y, what do we get? Oh, well, let's see. All of the x's are replaced with 1s, all the y's are replaced with 2's, so the first term turns into 2 cubed, which is 8, minus the second term turns into 4 squared, or 2 squared, which is 4, there we go, plus 3 times 1, plus 2 times 2, which is 4. So notice the 4's cancel and we get 11 right away. Nice. So the limit must be 11. That was good. So no exist, does not exist questions. Just plug in. I like that. I hope you like it as well. Well, I know you do. Now, this question is a little different. It says, where is the function f of xy equals x squared minus y squared over x squared plus y squared continuous? And we see that this is indeed a rational function, and all rational functions are continuous on their domain. So really what we're asking is, what is the domain of this function? And the domain of this function is essentially all values except for when the denominator is 0. Now the denominator, x squared plus y squared, we kind of saw this a little bit in the previous example. When is this equal to 0? Well, x squared is always positive, y squared is always positive. So there's no subtraction here, so there's no actual quality we can play with as far as algebra goes. But what we can certainly say is that when x and y are each equal to 0, then that actually holds. X squared plus y squared would be 0. So this is, well, basically what we're showing is that the point 0, 0 is not in the domain of this function. So where it's continuous is on its domain, which is a set of all x, y points, except when x and y are not 0. So that, I think, is one way to write that, and I'll call that set D for domain. So this is the answer here. The set of all points x, y, such that x and y are not 0. Actually, I'm just now noticing that this is a little ambiguous, because this kind of looks like x can be 0, cannot be 0, or y cannot be 0, but really I mean both of them. So maybe a better way of writing this is the point x, y is not equal to the point 0, 0. I think that makes a little more sense. All right. So now with that being said, now we can take a look at one more example, and then we'll move on to something a little different, which will involve functions in more than one variables as far as limits and continuity go. Okay, here we have two very similar functions, and I want to kind of compare them. So notice here we have either the function is the expression we saw previously that was discontinuous at the point 0, 0, but continuous everywhere else. And now this function is a piecewise function that is either this expression when the point isn't 0, 0, or 0 when it is 0, 0. Now, in fact, in this scenario, the domain is actually the whole two-dimensional space R2, because every value is okay. Here, the only point that wasn't okay was 0, 0, but we've now fixed that issue, so we created a new function that actually has all of R2 as its domain. But it actually is still the case, believe it or not, that this limit doesn't exist. In other words, the limit as xy goes to 0, 0 is not 0. So the value is 0, g of 0 is 0, 0, but the limit is not 0. So this doesn't actually approach 0, unfortunately. In fact, the limit here doesn't exist. So for that reason, this function is not continuous at 0, 0 still. So it is, let's say, discontinuous at 0, 0. So just capping a particular domain issue doesn't necessarily fix the continuity problem, is what I'm really trying to say with this example. And kind of like we saw previously, I mentioned that here the limit doesn't exist, and it's non-continuous, but just because it's not continuous doesn't mean the limit always doesn't exist. And here we see an example of that. So here we have 3x squared y over x squared plus y squared. And we saw this earlier, that this limit actually did exist and was 0. And if we notice here, this, similarly to this guy, has the same denominator, so this also has the same domain problem. But now fixing this, we have the domain of this function, similar to the domain of this piecewise defined function, is all of R2 now, and h of xy is actually continuous on the whole, on all of R2. And the reason why this is true is because this limit actually approaches what this approaches. Here, this had a limit that didn't exist, but here this limit is 0. And as it turns out, 0 is actually equal to h of 0, 0 now, because we defined that, meaning that h is actually continuous on all of R2. Awesome. So we see these kind of two examples, and hopefully this helps reveal more of what I was trying to say earlier as far as continuity versus, well, when it's not continuous. Now, here I want to discuss just a little bit about functions of more than two variables, and I use a kind of weird notation that we're kind of adopting from vector notation a bit. So here for limits, we have this precise definition of limit, which basically says that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. We want this to be true for all epsilon bigger than 0. And this implies that the limit as x goes to a of f of x is equal to L. So let me just say this right here is the definition for limit of f of x being equal to L, where x approaches a. And notice I'm using this vector notation, which I'll talk about in a moment. Now for continuity, f of x is continuous at the point x equals a if the limit as x approaches a of f of x is equal to f of a, so in other words DSP. So basically just what we saw before for definition of limit and for definition of continuity. But now here I see where x is the vector, n-dimensional vector x1 all the way to xn, and a is the n-dimensional vector a1 all the way to an. Now, we're using this notation here when we have essentially n components, or I guess you can say n variables for our function. So in reality, what I want to write is I want to write f of the vector x equal to f of x1, comma x2, comma all the way to xn. So we're just adopting that vector notation just to shorten things. Otherwise, these sentences would be huge. And in fact, notice I've already kind of shortened the sentences as well, if you kind of compare. So again, we won't really be talking about this too much. In fact, this is really going to mark the end of the video. But let's take a look at least one example. So let's consider this function over three variables x, y, and z. That's 1 over x squared plus y squared plus z squared minus 1. This function is actually continuous on every point in R3 except for what? Well, this is actually a rational function. And much like we saw for functions over two variables, functions over more than two variables actually has the same properties, as it turns out. In fact, a lot of it's pretty analogous. So this function, this rational function, is actually continuous on its domain. And its domain is a set of all values except for where its denominator is 0. And clearly you can tell that if you set the denominator equal to 0 and then add 1 to both sides, you get this. You get x squared plus y squared plus z squared equals 1. So what we're going to say is that this function is continuous on every point on R3 except for the points that satisfy this equation. So the set of all ordered triples x, y, z such that this is not the case. So such that this is not equal to 1. In other words, we're basically saying that this function is continuous for every point in R3 except for points that lie on the unit sphere. Because the unit sphere has equation x squared plus y squared plus z squared is equal to 1. So that's kind of interesting. So the domain of this would be, well, basically everything in three-dimensional space except for things on the sphere, and thus this would be continuous everywhere except for points on the sphere. But it gets a little funny because, again, in three-dimensional space, that would be the domain of this function. So it's really hard to imagine what this function would actually look like when you graph it in 4 dimensions. So have fun with that if you dare, but yeah, I'm not going to do that. So with that being said, that concludes our discussion on limits and continuity, and now we'll be pushing forward and describing more of calculus in 3 variables, well, in 3 dimensions really, and beyond, as we can clearly see here. So I'll see you in the next few videos. Really hope we enjoyed this, hope it was okay to understand. I hope I'm doing an okay job on explaining things. I know it's a lot of information, and I know, some of it is maybe easier to understand than other pieces, but anyways, with that being said, that again marks the end of the video. I'll see you in the next few videos. Thanks for watching, hope you enjoyed, and I'll see you then.